right, hello everybody. My name is Josh, and today I'm joined with Amog, and we are AP Tutor. So today we're going to take you through AP Physics 1 2018 free response questions, the official ones. And before we start today, I encourage you guys to pause the video and go to College Board's website, download the 2018 FRQs, and try them out for yourselves. It's 5 questions, not that bad. And then come back here, play the video, and see how you did. So we're going to start with question 1. So a spacecraft of mass m is in clockwise circular orbit of radius r around the Earth, as shown in the figure above. So the mass of the Earth is m sub e. In the figure below, draw and label the forces that act on the spacecraft. Each force must be represented by a distinct arrow starting on the spacecraft and pointing away from it. So obviously you can tell by the problem this is a free body diagram. So let's start by figuring out what forces are acting on the spacecraft. So we know that the force of gravity is acting on the spacecraft from the Earth. And looking at the setup of this problem, there doesn't seem to be any other forces. Also, since you're going in a circular orbit, so this is kind of your velocity, you're going in a circle around here, there has to be a centripetal force pointing to the center, and that has to be a net force. But since there's only one force, that has to be the net force. So we can draw something like this, pointing towards the center, and we'll label it force of gravity like that. That's all you need to get full credit on that part. Second part. Part B, derive an equation for the orbital period t of the spacecraft in terms of these variables and physical constants as appropriate. If you need to draw anything, you can, and don't add anything to the figure in part A. So we got that covered. So let's start with what we know. We know that there's a force on it, and that net force is the force of gravity. So by Newton's law of gravitation, we know that is big G times the mass of the Earth times the mass of your spacecraft divided by the radius squared. We also know that it is a centripetal force. So we know that's equal to mv squared over r. So we can do some quick cancellations, get rid of the m's on top, get rid of the r's and the r squared over there. And I'll just switch the sides so it looks cleaner. V squared is equal to g times the mass of the Earth over r. Now taking the square root of both sides, you can see that v is equal to square root of g m sub e over r. We don't have to worry about the negative sign because we know it's positive in this case. So now how does this help with the period? So let's just figure out our equation for speed in general. We know that speed is equal to distance over time. So the period is the time it takes to go one time around this entire circle. So your distance is going to be the entire circle, which is the circumference, divided by your period, the time it takes to go around that circumference. So we know that circumference is equal to 2 pi r, and the t can stay the same. Now we can multiply the t and divide the v, so we'll switch those. We know that t is equal to 2 pi r over v. And we can put this in, since we already know what v is, 2 pi r. And you see we're dividing by v. It's the same as multiplying by the reciprocal, so we can just multiply and flip these. So 2 pi r, so we're flipping, so the r goes on top, root r over g times the mass of the Earth. So that is our completed answer for the period. We can see that we have only this stuff in our equation and physical constants, so that's allowed. This will get you full credit. Part 2, a second spacecraft of mass 2m, so we're doubling the mass, is placed on a circular orbit with the same radius r. Is the orbital period of the second spacecraft greater than, less than, or equal to the first one? So they're putting a second spacecraft in here, so we can use our handy equation for period, since we got that from before. Same one works. So let's see, it's the same radius r, so this r is going to not going to change. This r is constant. Mass of the Earth, we assumed didn't really change. So because this small m, the mass of the spacecraft, doesn't appear in this equation at all, it doesn't matter. You can literally just say it's equal to. That's all the justification you need. Since it says briefly explain, we'll use words to do it. So on the actual AP exam, you could literally say something like this. The period of an orbiting spacecraft, as proved in the equation derived in the previous part, is not dependent on the mass. That's all you need to say. Therefore, it doesn't change. Don't say any more, don't say any less. This is all you have to say for the question. So for part C, this first spacecraft has now moved into a new circular orbit that has a radius greater than r, as shown in the figure below. But this time they're asking, is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original? So remember, we know our speed is equal to our distance over time, our circumference divided by our time. So we can substitute our handy equation for a period. Root r over g times the mass of the earth. So we have it's the same thing on the bottom. We can cancel it out. And finishing. So as you can see, r did increase, which means this is going to go up over here. However, since we're also in the denominator, it's inversely proportional. So v will go down. You could see that since this increased, this whole thing's going to increase, and this is going to decrease. So you would put less than. Again, it says briefly explain your reasoning. So you could say something like this. The speed of your spacecraft, as proved in the derivation in part B, decreases with an increasing orbital radius. You can kind of see how we did the same thing over here. So now Amog will take you through part 2.
Hey guys, I'm Amog, and I'm going to be solving the next 2 FRQs. So question 2 is going to be an experimental design and graphing FRQ, in which a group of students are preparing a large batch of conductive dough, molding the dough into cylinders, and then applying the potential difference to determine the resistance of the cylinder. Below, we're provided with a table which contains the results of their experiments, and then we move on to the first part of the question, A1, in which the students want to determine the resistivity of the dough cylinders. So we want to be graphing in this question. And so we first need to indicate the quantities which can be graphed to determine the value for the resistivity of the cylinder. So an equation that contains all the quantities that are provided in the table would be resistance equals the resistivity times the length over the area. Now, you know that whenever we're doing a graph, we always want to graph it in the form y equals mx plus b. And if we look at our 2 equations, we can see that there is no y-intercept on this, so we can cross that out. The resistance corresponds to y, so we know resistance will go on our vertical axis. And since we'll want resistivity to be our slope, we're left with length over area, which we can graph on our horizontal axes. And since the units are meters over meter squared, we can cancel that out and get units of 1 over meter. In part A2, we want to actually graph it. So we know from our equation, which we're going to be graphing, resistance equals resistivity times length over area as determined before, that we have our quantities, resistance and length over area. So if we look at our table, we see that resistance has its own column, but then length and area are 2 separate columns. So it's always a good practice to just just quickly get out the data for length over area. And so always do that before you graph if there's a quantity that isn't explicitly stated. So now we're going to be actually graphing the values. So the first thing we should always do is label our axes. And then we should label our y-axis. Now we have to split up our graph into sub-intervals that match the table and that are possible to graph. So it's always best to try and graph as many, use as much of the graph as you can. So considering that our x-axis goes up to 260, which is a bit over 250, and we have around 6 different, lines, we can always start with 0, and then we can go in sub-intervals of 50. We can do the same for our y-axis. Now we're going to go ahead and graph our points. And now we should draw a best fit line that contains the most of the points, starting from 0, and then going up to the final point, but not beyond it. So that's our graph. And then in part 3, we need to use the above graph to determine the value for the resistivity of the dough cylinders. So if we remember, the slope is equal to the resistivity, so we should find the slope using the slope equation. And then pick 2 points on the graph. And since our resistivity equals the slope, our resistivity will equal 0.378 ohm meters, which is the units of resistivity. And that's part A complete. In part B, another group of students are performing a similar experiment, except this time they're shaping the dough into long rectangular shapes instead of cylinders. Now, it's important to realize that they're asking for resistivity and not resistance. And we know that resistivity is simply based on the material of the object and not the actual shape of the object. So no, it will not affect the value of the resistivity determined by the students. On the AP exam, you can write an explanation, a justification as simple as this, and that can earn you full credit. Part C is our experimental procedure, and here we need to determine whether or not the resistivity of the cylinders depends on the temperature of the dough. So we first should find out our independent, dependent, and controlled variables. So we know that the independent variable is going to be temperature, since that's what we want to know if it has an effect. Our dependent variable is going to be the resistivity. And then some of our controlled variables. So similar to how the students did in part A, we're going to be applying a voltage to the cylinder so we can determine the current. And then we know that resistance is equal to resistivity times length over area. So using Ohm's law and the equation for resistivity, we can find that the variables that will have to be controlled are voltage, because in this equation, that's the independent and this is the dependent. And then here we want resistance to be controlled, which we want length to be controlled and area to be controlled, sorry. So those are the variables we want to be controlled. And now we can write a setup using equipment we have in a normal physics laboratory. So an example procedure is we construct 3 different cylinders out of the dough with the same length and cross-sectional area, keeping those 2 variables constant. Then we keep one dough at room temperature, heat another cylinder, and then cool another cylinder. So we have different ranges of temperatures, which is our independent variable. Then we apply the same controlled variable voltage to the ends of each cylinder, and we can measure this with precision using a voltmeter. And then we measure the current through each cylinder using an ammeter. If the current changes for each and every one of them, since the length and area are changed, that means the resistance can only be changing because of the resistivity, which means it has an effect on the resistivity. And if the current is not changing, then that means the resistivity has no effect. And this is a pretty good example of a procedure that you can write and get full credit for. Okay, so now we're going to be solving FRQ number 3. We have a disk that's spinning about its axle, and a student's experiments reveal that while the disk is spinning, there's friction between the axle and the disk, which is exerting a constant torque on the disk. So at time t equals 0, the disk has an initial counterclockwise angular velocity omega naught, which in terms of our graphing is positive, and the disk comes to rest at times t equals t1. On the grid left below, we want to sketch a graph that represents the disk's angular velocity as a function of time, from time t equals 0 to time t equals 1. So the first thing we can do is write down that we know sigma torque equals I alpha. Since there's only the torque exerted by the frictional force on the disk, that's the only thing that's causing an angular acceleration. And we know that's going to be negative since it's decreasing the angular velocity over time. And since we know that acceleration is equal to the change in angular velocity over time, a constant negative angular acceleration is going to result in a negative angular velocity. And since we know that the acceleration is constant, we can start by graphing our initial angular velocity and our final. And as I said, it's constant, so we can just draw a line connecting these 2 points. Now, we know that the angular acceleration is going to be constant and negative, so it's going to have to be underneath the x-axis on this graph, and we can put it at any point on the graph as long as it's constant the entire time and it's negative the entire time. In part B, the magnitude of the frictional torque exerted on the disk is tau naught, and we want to derive an equation for the rotational inertia of the disk. So we can start once again by writing out sigma torque equals I alpha. And then we know that there's a torque, tau naught equals I alpha. Once again, we know that angular acceleration equals the change in angular velocity over time. we know that the initial angular velocity is omega naught and the final is 0. And the total time is t1. So it's going to be negative omega naught because 0 minus omega naught and 0 disappears over t1. We can plug that back into our equation. We have tau naught equals I times negative omega naught over t1. And then finally, we can rearrange. And we get that the moment of inertia is equal to the torque times the time over the initial angular velocity. In part C, we have once again our graphs, except this time, at time t equals 1/2 of t1, so around here, the student starts dripping oil onto the surface to reduce the friction. So the friction is going to be decreasing over time. And as time passes, more oil reaches the contact surface, which is reducing the friction further. So we know that from time t equals 0 to t equals t1, 1/2 t1, it's going to be the same as our past graph. So we can go ahead and just draw that in on both of our graphs. Except now, over time, not just the angular velocity is going to be decreasing, but our angular acceleration is going to be decreasing since the torque exerted by the friction is decreasing. We know that angular acceleration is equal to the change in angular velocity over time. So if the angular acceleration is decreasing, then that means that the angular velocity is still going to be decreasing, but at a decreasing rate. So we can explain this by, we know that acceleration is the slope of the velocity graph. And since the acceleration is decreasing, the slope of the velocity graph is also decreasing over time. So that's going to become sort of a curve. That was an okay curve. I'm not the best artist, but here they're not judging you on your art skills, and they're more judging you on whether you can show it out. So if we want to get a better graph, that might be a better idea. It will probably look something like this. Yeah, because the rate at which the angular velocity is decreasing is also decreasing. Now, we know that the acceleration is going to be decreasing at a constant rate, and it's going to go up, but this means that the magnitude of the acceleration is still decreasing at a constant rate. So it's going to look something like this. And then finally, in part D, the student now wants to mathematically model the magnitude of the torque exerted by the axle on the disc. So he writes down two of the following equations, each which includes a constant and appropriate unit. We want to figure out which equation better models the experiment. So we can forget about the units since we're looking for proportionality here. And we can see that in the first equation, we have that torque is directly proportional to the time. So as the time increases, the torque also decreases. And in equation 2, it's inversely proportional. So as time increases, torque decreases. Now, over time, more oil is being put onto the axle, so which means the frictional force is decreasing, and so the torque is decreasing with time as time increases. So that means equation 2 mathematically models the experiment. And we can write that out just as such. The more oil that drips onto the axle results into the force of friction decreasing, and since the frictional torque is decreasing over time, and equation 2 models that relationship better. Now I'll pass it back over to Josh for the remaining two free-response questions.
So yep, I'm back and I'm taking it through number 4. And this sounds like a fun waves problem. So a transverse wave is traveling to the right along a string. Two dots have been painted on the string, so we could see dot P and dot Q are on the string. So this is the string at an instant in time. At this instant shown, dot P has maximum displacement, so it's far from equilibrium, and dot Q has 0 displacement, so dot Q is on the equilibrium line. At each of the dots P and Q, draw an arrow indicating the direction of the instantaneous velocity of that dot. If either dot has 0 velocity, write V equals 0 next to the dot. So remember, for each point on this string, there is always going to be a restoring force towards equilibrium. So as we can see, dot Q, before this instant in time, dot Q was over here. But now dot Q has been moved over here by a force. And at equilibrium, that force has no magnitude. But the farther you get, it will. In fact, every piece of this string is undergoing simple harmonic motion, and we can treat it as such, with this line being equilibrium. So if we look at dot P, let's think about this in terms of energy, for example. So when you're at the maximum displacement from equilibrium, you're all potential energy. There's no kinetic energy. It's all potential stored in the restoring force of the string. You could say that's kind of tension. So if dot P has max potential energy, it has no kinetic energy. And if you have no kinetic energy, you're not moving. You have no speed. So we could literally write V equals 0. Dot Q is kind of in the opposite spot right now. Since it's at equilibrium, it has no potential energy since your restoring force is proportional to kx and x is 0. You have no force. It's not accelerating. You have no potential energy. It's right in the middle. So you have maximum kinetic energy. So you're going to have a speed. You're going to have your max speed in the whole thing. So what's the direction of this velocity vector that we have to draw? Since it's asking you to draw the arrow. So let's think about it. Since the wave is going this way to the right, dot Q used to be here, but now it's here, and it's going to be going up there. So dot Q is going to be moving right here. Remember, the wave moves to the right, and since it's transverse, by definition, each piece of the wave is going to be moving up and down. So that's it for part 1. Now part 2 is kind of an interesting one. It's kind of the same idea, except instead of velocity, we're using acceleration. So let's look at dot P first. The general idea here, as I said, your restoring force on this string is going to be proportional to kx. This just means proportional. So since you see dot P is the maximum distance, it's maximum displacement from equilibrium. So x, your distance from equilibrium, is going to be very, very high. So then your force is very, very high. And if your net force is high, your acceleration is very, very high. So as usual, it's going to pull you towards the equilibrium point. So that's going to be your acceleration vector for P. Let's talk about Q though. So as usual, we know it's proportional to kx. But since Q is at equilibrium, you're not far from equilibrium. In fact, your distance from equilibrium is going to be 0. So that is 0. So this is 0. When you have 0 net force, you have 0 acceleration. So you can move on to the next one. It looks like a graph. So the figure below represents the string at times t equals 0. The same instant as shown in part A when dot P is at maximum displacement. So you could see this, our new equilibrium line, is the x-axis. And for simplicity, dot Q is not shown. So that's good. We won't have to deal with dot Q now. On the grid below, draw the string at a later time. T is equal to the period over 4. So we're just drawing the same thing here, except 1/4 of the period later. So let's talk about what this graph is. This graph is the wave at time t equals 0. It's also the wave at time t is equal to the period, because the period is literally defined as the time it takes for the wave to get back to where you started. In fact, the period of anything is the time it takes to get back to where you started. So this is the same exact graph as when you started. But instead they're not asking us to draw a t, they're asking us to draw a t over 4. And since we only have y versus x, there's no t anywhere. So we're gonna have to figure this out ourselves. So let's start by figuring out the wavelength of the wave. So we're starting here, we'll go up, we'll go back down, and here. This dot right here. So the distance between this from 0 to 24 centimeters is your wavelength. And remember, your period is the time it takes to get back. So the period is the time it takes to do this whole wavelength. And since they're asking for t over 4, we have to find 1/4 of these 4 boxes. You can see 1, 2, 3, 4. So 1/4 will just be 1 box. Since the wave is moving to the right, we just have to move the wave to the right 1 box, which means we're going to move every point on the wave to the right 1 box. So this point is going to go here. This point is going to go here. And you should be able to see a pattern as I draw more and more of these. Hopefully you can see the intuition behind this. And we're almost done. Let's just draw the ones at the beginning too. So our wave is going to kind of look something like this. I know this isn't the best wave, the best drawing skills. But remember, the AP exam isn't looking for your artistic ability, and I'm not really drawing on paper right now, so give me some slack. And they said to draw it on this grid, so we'll just redraw our new wave on this grid. When you're taking the real AP exam, you shouldn't really draw in here. I was just drawing to illustrate the example, but you'll know what you're doing. So now part 2, on the drawing above, draw a dot to indicate the position of dot P on the string at the same time as we drew this. And clearly label the dot with the letter P. So remember what I was saying before, dot P is undergoing simple harmonic motion. It's moving down, it's gonna move up and down and back and forth again. But what doesn't change, it's gonna keep moving on this line. In fact, we know it's a transverse wave, right? So the direction of the wave is always going to be perpendicular to the direction of where each piece of string is going to move. So this is kind of like a 90-degree angle right here. So we know that dot P is going to be moving all along this line. So this part 2 is basically as simple as finding the new position of dot P. Since we know that dot P is on this line and on this wave, we just look for the intersection of this. And we can just draw that here and label it with letter P. And that's dot P on our new wave. Again, this is not the best wave, but they're not looking for that kind of stuff on the AP exam. And finally, now consider the wave at time t is equal to the period. Determine the distance traveled, not displacement, by dot P between times t equals 0 and t is equal to the period. So again, this is the same thing we saw before. This is the graph at t is equal to 0 and the graph at t is equal to the period. Now, if they're asking for displacement, we know that since you're starting and ending at the same spot, your displacement is going to be 0. But they're not asking for displacement, they're asking for distance. So this is irrelevant. Instead, we have to figure out what is dot P doing in between 0 and the period. So we can look at that. We know it's going simple harmonic motion up and down. It's going to start here, then it's going to have kinetic energy here and potential energy back up here. So we know it goes up and back down. So this is 8 and this is 8. So that would be 16 centimeters. Remember, watch your units. Up and 16 centimeters back down, which is equal to 32 centimeters. And that would be your answer. Remember, distance is a scalar, not a vector, so there would be no direction on this. And that's it for FRQ number 4. All right, so this is number 5. It's the last one in 2018 FRQ, so let's push through this. Now, block P, this is block P, of mass M is on a horizontal frictionless surface. So this is our horizontal frictionless surface, and it's attached to a spring with spring constant K. The block is oscillating with period TP and amplitude AP about the spring's equilibrium position right here, x naught. A second block of mass Q with double the mass, 2m, is then dropped from rest and lands on block P the instant it passes through equilibrium, as shown above. Block Q immediately sticks to the top of block P. The two-block system oscillates with period TPQ and amplitude APQ. So now determine the numerical value of this ratio, the new period over the old period. Big thing to notice here, big thing to notice. It says numerical, which means stuff's going to cancel out, so your answer is going to be a number with no variables in it. Maybe a constant, but no variables in it, just numbers. So let's figure out. We know this is in simple harmonic motion since it's oscillating. So we know the formula for simple harmonic motion oscillation, the period is going to be equal to 2 pi times the square root of the mass oscillating over your spring constant. That's good. That's all we need for that. And our new period for PQ is going to be 2 pi. So what's our new mass now? We know that the total mass is going to be MP plus MQ. So that's M plus 2M, which is going to be 3M. 3M, and the spring hasn't changed at all, so we're going to keep the K. And this is just as simple as dividing TPQ over TP. New period over old period. So we're going to use 2 pi root 3M over K divided by 2 pi root M over K. Now these go, since they're both the same. Cancel that. And we can use square root properties to split up the square root 3 and the square root M over K. You guys can probably see where I'm going with this. Get rid of this, get rid of this. As I said, stuff cancels and you're left with the square root of 3. That is a numerical ratio, and something like this would earn you full credit on the AP exam. Now for the next part, part B. The figure is reproduced above. How does the amplitude of the oscillation of the two-block system compare with the original amplitude of the block alone? All right, let's think about this. So if we know from the previous problem that the period, since root 3 is bigger than 1, the period is going to increase. And since we know that the speed of your movement is going to be inversely proportional to the period, you can say that since the period went up, the speed went down. So speed went down. And now we can kind of switch in terms of energy. So now that this block has hit this block, we're going to define our system as the spring and the two blocks. So you can draw a little system barrier here. I find that better to visualize it with a system, with a little box around your system, tell you what your system is. So now, since we know our system is a spring and these two blocks, there's no friction. The only net force acting on our system is 0. Since the gravity and normal force are going to cancel out and there's no forces, there's no friction or anything, energy is going to be conserved. So since your velocity went down, you know that your kinetic energy went down. Since kinetic energy is equal to 1/2 mv squared. So now you say that m went down, but v is squared, so it counts for more. So now we know that you're at equilibrium. So you have no potential energy. Your total energy is completely based in kinetic energy, like so. And since this went down, your total energy went down. So then you go from here and you go to your amplitude of oscillation. Your amplitude is going to be at the end when your energy is completely potential energy at the end. And that's equal to 1/2 times k times a squared. So since this went down, and you know that we didn't change the spring, k stays the same. You know that the amplitude went down. So you can use that to say the amplitude of the new system is going to be less than the old system. And there are other ways you can do this. Like I'll show you another example. You can actually use the collision between the two blocks over here. Say that momentum is conserved since no external forces are acting on the system at the instant of equilibrium. You can see that. At equilibrium, the total energy of the oscillating system is completely kinetic energy. We know that since we're at equilibrium. So after the collision, due to conservation of momentum, the velocity of oscillation must be decreased. We know that because we can set up that momentum initial equals momentum final. mv naught is equal to 3m vf. So we know that because there's a 3 here, vf is definitely less than v naught. So you can say that. Through calculations, this is determined to be 1/3 of the original velocity. Actually, you don't have to say this. As long as you know that velocity went down, that's all you have to know. So in a real coherent paragraph length response in the real AP exam, this is not necessary. Following the collision, energy is conserved. We know that, no external forces. Although the mass has increased, the equilibrium kinetic energy has decreased. So that here, remember, you see that this counts for more. We found that the system's overall energy has decreased. Since the spring constant remains the same, the amplitude of the new system must be less than the original. And we got that here. One thing I wanted to point out is that anytime you see these, it's gonna be the same on any AP exam. A clear, coherent paragraph length response. This means you're dealing with a paragraph response question. And there's one point that's given on every AP exam. One point you can easily snag for just having a coherent paragraph. That means like not doing things like this. I mean, they won't take off points if you have it, but a big thing that students make, a big mistake that students make a lot is saying more than they have to. And especially when you start saying more and more, you tend to say things that might not be true in the problem. And that can cause you to lose points. But on a real AP exam, this would earn you full credit. So with this, they're both slightly different methods of solving the problem, but they both get you where you need to go. So thanks for watching, guys. If you like what you see, please give us a thumbs up and subscribe. If you have any requests for other videos you want to do, anything with AP Physics 1 or the other APs we cover, you can check out our channel or leave a comment down below in the video.
And we'll be linking the original college board solutions down below so you can see what exactly they would assign points for if you want more of a in-depth review.